So welcome back to the Non-Commutative Geometry and Topology seminar. Today's speaker is Fabio Gavarini from Tor Vergata, University of Rome Tor Vergata, and he's going to talk about quantum group deformations and quantum arc matrices via the quantum duality principle. Please.
Thanks, Andrea, and thanks to the organizers for inviting me to this seminar. It's my third time in Prague, but I think it's the first time I talk in this very seminar. Otherwise, the other times were conferences. Now, let me stress also that I'm reporting on a joint work with Gaston Garcia from La Plata in Argentina. The title is very daring. I will mostly speak of quantum group deformations. Let's say quantum arc matrices entered the game as a special case, in a sense. On the other hand, I first worked almost 30 years ago on quantum arc matrices, and then when working on this paper, I realized that it was a sort of generalization of that story. So the two arguments actually fit together well in a single talk. Good. So what is the plan of the talk? I'll be sketchy on this first introduction. The main goal is to study deformations for quantum groups and for their semiclassical limits. Well, deformations means the following. It's an algebraic technique which applies to Hopf algebras on the one side and Lie algebras on the other side. You have two kinds of deformations, deformations by twist, deformations by two co-cycles. Either one of them affects only half the structure. So you have a Hopf algebra, you have a product and a coproduct, so two halves of your total structure. And similarly in the Lie algebra setting. What do we expect? Let's say we have a quantum level where you work with the Hopf algebras and the semiclassical level where you deal with Lie algebras. Then in these cases, we use some tools to perform deformations, which are these twists or two co-cycles. So first we expect that twists for the quantum level, let's say for quantum groups, when specialized in a proper sense to h equal to 0, gives rise to twist or two co-cycles for the Lie algebras, which gives us the semiclassical limit of the quantum objects. Then once we have this, we might take the specialization limit, that is, we fix our deformation parameter h to 0. If you think in terms of like parameter q, you are setting q equal to 1 if you want, and you recover classical objects. Then we expect that if we had begun from a deformation of a quantum group using some deformation object like a twist or a two co-cycle, then when we perform this specialization, the object that we find is again a deformation of the previous semiclassical limit, deformation carried on using the semiclassical limit of the previous deforming object. That's the idea. Okay, now the memo on semiclassical structure has been kindly implemented by Jan, so I just fix here the terminology. So Lie algebra will be a triple where you have an underlying vector space endowed with the Lie algebra structure given by some Lie bracket, a Lie coalgebra structure given by this Lie co-bracket small delta, and then you have compatibility conditions among the two structures. Essentially, the Lie co-bracket has to be a two co-cycle in the sense of the Lie algebraic structure. And if you compare your Lie algebra with the universal enveloping algebra, the point is that having a Lie co-bracket amounts to be the same as having, write it with the same symbol, a Poisson co-bracket for the universal enveloping algebra. The point is, once you have the Lie co-bracket, it extends uniquely to a Poisson co-bracket. And conversely, if you have a Poisson co-bracket and you restrict it to the Lie algebra, then it is also obliged to fall within G tensor G. So in the end, it's a Lie co-bracket. Good. You have the global counterpart. Instead of looking infinitesimally at a Lie algebra, which might be a Lie algebra, you look at, say, algebraic group. And then The algebraic group might be a Poisson algebraic group, and this means that we endow it with an additional piece of structure, which is this Poisson bracket. Now, given by these brackets, which has to be compatible with the Hopf structure, as Jan explained. We have a weaker, somehow generalized notion of formal Poisson group, which is a formal group. You're just taking, instead of a whole group as a geometrical object, just a local neighborhood of the identity element. And you are also adding a Poisson structure on it. So you can realize this object algebraically as being a function algebra in a generalized sense. So your functions are actually formal series in some parameters that you can realize as local parameters around the identity element. So in terms of purely algebraic terms, you might think that you are taking originally a true algebraic group with its function algebra. Then you take the augmentational ideal, which defines the identity element, and you take the completion, the added completion for this ideal. It is also important to notice that in this case, your algebra of functions on the formal group is the same, identifies with the full dual of the universal enveloping algebra. And conversely, you can recover the universal enveloping algebra as being the topological dual of the formal group. Topological dual means you are taking the linear functionals, which are also continuous with respect to the adic topology on this algebra.
So usually you take the linear dual will not get a Hopf, right? But here you're saying that the linear dual usually is again Hopf.
It's again Hopf, still in a topological sense.
Take the finite dual.
Let's say your FG is formal series in some set of variables. The tensor squares you end up in with the coproduct will be formal series in two sets of variables. But formal series, not just formal series times in a first set times formal series in a second set. That's why you need taking again a completion. Good. And now it's time to switch to quantum groups. So at the quantum level, as Jan sketched before, by quantized universal enveloping algebra, I mean a topological algebra defined over the ring of formal series in one parameter, which is the so-called deformation parameter. What we ask to this object is to have a special limit, that is when we set h equal to 0, then you get something isomorphic to u of g. So here in the notation for the quantized universal enveloping algebra, I say enclose the G to remind me that the semi-classical limit is given by this Lie algebra. And actually it's more than a Lie algebra because, again, as Jan mentioned, you inherit from the quantization a Poisson cobracket for the universal enveloping algebra, which, as I said, boils down to having a Lie cobracket for the Lie algebra. So the Lie algebra is actually a Lie bialgebra, just because it has some quantization. The dual picture is with a dual quantum object. So the dual quantum object here is a quantized formal series of algebra. The idea is to have a quantum version of the formal series algebra, which describes a formal group. So this, again, is a Hopf algebra, topological in a slightly different sense. This time, the topology for which it has to be complete is the topology defined by the ideal generated by the deformation parameter h and, say, local parameters around the unit element. So you have two kinds of parameters with respect to which you consider a completion. The geometrical ones, which already exist and are taken into account in the classical setup. And additionally, you have this deformation parameter. In the case of a quantized universal enveloping algebra, instead, you only need the deformation parameter. Now, in this case, again, we have a Poisson structures which comes automatically from the quantization. This time, you see the formula is pretty dual to the previous one. Here, you get the cobracket because you compare the coproduct at the quantum level with the opposite coproduct, where you just switch the the two terms in a tensor product, you know that modulo H, this is 0, because in the universal enveloping algebra, the coproduct is co-commutative. No? So being 0 modulo H means that it is H times something. So you can divide out by H and you take the limit. Here you do the same with the multiplication. We know that in the classical formal group, FG series, the product is commutative, which means that at the quantum level, you have something which is commutative modulo H. So this difference above is H times something. You divide out the H and you take the semi-classical limit of the something which is there. And this gives you automatically a Poisson bracket. It's much easier to see because this difference above is nothing but a standard commutator in associative algebra. So it is a Lie bracket. Additionally, it also enjoys the Leibniz properties with respect to the associative product. So you have already a Poisson bracket at the level of the quantum algebra. And then you take its core at the semi-classical level by dividing out and taking the limit. Great. So now again, the very definitions, especially the second one, are made in such a way that these two notions are dual to each other. So in which sense? If I'm taking a quantized universal enveloping algebra, this object on the left, and I take its full linear dual, here the topology is the H-adic topology. So whatever linear functional is automatically continuous for the H-adic topology. And what you get is can be seen as being exactly a quantum formal series algebra whose semi-classical limit will be a formal group corresponding to this Lie bialgebra. Here instead we're taking a quantum formal series of algebra and we're choosing again a topological dual, which means you're taking linear functionals which are continuous with respect to the topology. And then you get back an object which is automatically co-commutative modulo H and turns out to be a quantized universal enveloping algebra whose semi-classical limit will be exactly the Lie algebra associated with this group. Actually, the Lie bialgebra associated with this formal Poisson group. Essentially, you are lifting to the quantum level the duality that already exists at the classical level between universal enveloping algebras and formal groups. In a sense, the definitions are made so that this happens. Great. So now it's time to switch to the main character in this story, which is the technique of deformations. As I said, it's a standard technique. We see first the Hopf algebraic setup. Let's say you start with a Hopf algebra, possibly in some generalized tensor category, topological, whatever. Okay, a twist will be an element in the tensor square enjoying these three properties related, as you see, with the co-unit. The property T2 is sort of a normalization condition. And the third property is connected with the coproduct. You have a dual notion in the sense of duality. The dual notion introduces what are called two cocycles. The name is due to the fact that there's some cohomology around. So a two cocycle will be an object in the dual of the tensor square, which has to obey these three conditions. Now I have written them here in terms of values on single elements. But if you write them properly, these are exactly the dual conditions in the dual category to those I wrote for a twist. So in short, somewhat roughly speaking, an element is a two cocycle for a Hopf algebra if and only if it is a twist for the dual Hopf algebra, and vice versa. An element is a twist if and only if it is a two cocycle for the dual Hopf algebra. Up to giving a correct meaning to dual Hopf algebra and so on and so forth. Good. Now the use for this object is to apply them and perform deformations. So here is the recipe. Let's say we start with a Hopf algebra and you take a twist or a two cocycle. If you are taking a twist, then you keep H as an algebra with its algebraic structure, and you introduce a new map, this delta to the F, defined as the old coproduct followed by conjugation by the twist. This is again a map from H to its tensor square. So it looks like a coproduct, and it actually is again a co-associative coproduct, and it is again compatible with the old algebraic structure. So you end up with a new Hopf algebraic structure with the same circle as algebra, which you denote by HF. This is the deformation of H by the twist. The dual construction, of course, is with a two cocycle. This time you keep H as a coalgebra with the old coalgebraic structure. You introduce a new multiplication map given in this way. As you can see, the recipe reads the same. Here the product written here, the star, is the convolution product. And this map looks like a multiplication map. Actually, it is an associative product, and it is again compatible with the old coproduct. So you have a new Hopf algebraic structure denoted by H sub sigma, which is called the deformation of H by the two cocycle. So in either case, you modify just half the structure, depending on the kind of element you're using, the kind of deformations you are performing. By the way, if you look at the recipe, you see that sometimes these recipes, okay, they do make sense, but the outcome is totally trivial. Let's say for the first case, the twist deformation, if you're starting with a commutative Hopf algebra, then the tensor square is commutative as well. And then in this recipe here, conjugating by F is meaningless. So the new coproduct actually coincides with the old one. So for commutative Hopf algebras, you might perform deformations by twist, but it gives you nothing. Any deformation by twist is trivial. So, for instance, for Hopf algebras coming as functions over some group or functions over a formal group, there is no need, no meaning to perform deformations by twist. And that's why for this kind of objects, you only find in literature people looking for deformations by two cocycles, which makes sense. And similarly, if your algebra is co-commutative, then performing deformations by two cocycle gives you nothing new. And that's the case, for instance, for a universal enveloping algebra. Good. We'll see in a moment why this is relevant. What happens in the semi-classical world? Well, let's say now instead of Hopf algebras, we are taking Lebesgue algebras. That's technical, but let's say you have a similar picture. So you can consider elements called twist or two cocycles. The twist is an element in the tensor square of your Lebesgue algebra G, which has to obey these two kinds of conditions. The two cocycle is something in the dual of the tensor square obeying these two conditions. Again, the definitions are cooked up, say, so to be dual to each other. So again, let's say an element for G is a twist if and only if it is a two cocycle for the dual Lebesgue algebra. And conversely. Why do you use these elements? Again, to define deformations. So I start with a Lebesgue algebra, I pick a twist or a two cocycle. If I take a twist, then in this case, I keep untouched half the structure, the Lie algebraic structure. Now on this old Lie algebra, I introduce a new Lie cobracket given by this formula. So you see here you have the old Lie cobracket, you are modifying it by this term. And this happens to be, again, a Lie cobracket, a new Lie cobracket which still is compatible with the old Lie bracket. So you have a new Lie bialgebra structure which coincides with the old one for the Lie bracket, but it's different for the Lie cobracket side. The dual construction uses two cocycles. These times you keep the old Lie cobracket, so you stand with the same Lie coalgebra. You're introducing a new Lie bracket. The new Lie bracket here is given by the old Lie bracket plus these two additional terms, which uses the two cocycle gamma. So again, you're modifying half the structure, and you still get a new Lie bialgebra where what's new is the Lie bracket, depending on your two cocycle. Again, the two constructions are clearly designed so to be dual to each other. The two recipes are dual to each other. But again, we have some trivial cases. So In the first case, when you perform deformations by twist, if your original Lie algebra is abelian, since here in the definition of the new deformed Lie co-bracket, you're using the adjoint action, this is trivial as soon as your Lie bracket was trivial, and so you have no deformations by twist. And similarly, if the Lie algebra is co-abelian, then you have no deformations, no non-trivial deformations by two cocycle. Good. And now it's time to somehow relate the two words, the upper word of quantum groups and the downwards word of semi-classical structures. We have globally a picture with four possible actions. Say we might deform by twist or by two cocycle, either a quantized universal enveloping algebra or a quantized formal series of algebra. Now, actually, the story is different depending on what you are trying to do. Half of the story is essentially easygoing, namely deforming a quantum universal enveloping algebra by twist, which is, say, the natural choice, what people did at first attempt, or dually deforming quantum formal series of algebras, quantum functional algebras, if you want, by two cocycles. Instead, it is much harder because it's not at all natural. I mean, if you, the first attempt you might try gives you trivial outcome, and that's because it will be trivial semi-classically. So you have to cook up something new and invent something new. And you do find something new, which is, I mean, you can find it by hand computations, but has a deeper motivations given by quantum duality principle. That's the core of our work. So let's start with the easy cases. Let's say I'm taking a quantized universal enveloping algebra and a twist for it in the standard sense. This twist has to be trivial modulo H. Why? Because this means that actually at the semi-classical level, we are deforming nothing. We are really deforming something at the quantum level. We are focusing on what happens at the quantum level, just to divide what happens at the semi-classical level and what happens at the quantum level. Okay, once your twist is written, appears in this form, 1 plus something, 1 plus h something, you can write it as an exponential of this form. Just take as k this element. By assumption, these elements lives inside this HID completion. So all of this makes sense. Great. So this makes sense. And then first result. This object C sub k is sort of the semi-classical limit of this k, or the logarithm, so to say, of my twist. Actually, I'm taking the antisymmetric part because this is the only part which enters really the game. Okay, the point is, this happens to be a twist element for the underlying Lie algebra. So you see, what I expected as first result was that a twist or a two cocycle at the quantum level should have a semi-classical limit of the same type at the semi-classical level. Okay, that's true in this case. And now I have a twist at the quantum level, I have a twist at the semi-classical level. I might compare what happens with deformations at both levels. Okay, that's the second point. In this step, I'm taking the deformations by twist at the quantum level. And what I find is that this is, again, a quantized universal enveloping algebra, not just a off algebra. So it has some semi-classical limit, which is a Lie algebra. And this Lie algebra happens to be exactly the one that you find if you deform the original semi-classical limit G using this twist for the Lie algebra. In short, here I wrote, if I specialize, if I take the semi-classical limit of these quantum deformed objects, what I take is the deformed objects at the semi-classical level. In other words, let's say quantum deformations followed by specialization is the same as specialization for the twist followed by deformation. So in a sense, deformations and quantization commute. Wait, just a quick idea of the proof. It's essentially a bookkeeping business. So you have your twist. You expand it as a series in H. So let's say the first order term is this K. Wait, now my F is a twist, so it has to obey some conditions, some equations. Okay, write the equations after expanding in H. And I read the equations at the different orders of H. At order 1, essentially, I find a condition for K, which says that this K has to obey an equation of the form Tk equal to 0. Great. Now I look at the condition Tk equal to 0 with respect to the coproduct. And this tells me that my K, in principle, is something living in the tensor square of Ug with itself. But actually, it lives in the tensor square of G with itself, which is exactly the space where you look for twists. And now you have this object K, which lives in the right space, Ck. Again, looking at the equation at H equal to 0, you find, long story short, that these conditions turns out to be the conditions that tell you that this Ck is a twist in the Lie bialgebraic sense. Okay, now I do have the first step, claim A. This Ck is a twist for the Lie bialgebra, so it makes sense to compare the specialization of the quantum deformed object with the deformation of the semi-classical object. And essentially, you make this computation. That is, you have to compare the Lie cobracket coming from here with the deformed Lie cobracket there. Now, the Lie cobracket coming from here, you have a recipe for it. You have to take the coproduct, take the difference with the opposite coproduct, and divide out H and specialize. Okay, you compute it, taking into account that this is your new coproduct, and you find out this equality, essentially. Okay, let me maybe quickly mention what happens at the dual level. Okay, let's say you have now a quantum formal series of algebra, quantum function algebra, you might think, if you are more familiar with that. You take a two-core cycle, but you look at two-core cycle which are trivial modulo H. So they start with 1. In this setup, 1 is the tensor square of the co-unit map. So as it starts with 1, like here, I can write this the exponential of H something. And again, this something, this zeta, happens to define, there are some intermediate steps, but happens to define a two-core cycle for G star. Let me mention that if I'm starting with a quantum object of this kind, I do know that G is a Poisson formal group. So the tangent algebra is actually a tangent Lie bialgebra. So the dual space is a Lie bialgebra as well. So this makes sense. Now, you perform the formation of the quantum object, and it happens to be, again, a quantum formal series of algebra. So you study its semi-classical limit. It is some formal Poisson group. Great. Now you look at the associated tangent Lie bialgebra, and you find out that it is exactly our the dual of our original, the cotangent Lie bialgebra here, but now it has the same Lie cobracket, but a new Lie bracket. And this new Lie bracket is exactly what comes when we perform the formation by two-core cycle at this level here. So again, the idea of the proof is like before, that is, for claim A, you have to realize that this object is sort of some two-core cycle for this G star. So you expand the initial two-core cycle for the Hopf algebra you are starting with. You expand it with respect to the deformation parameter as a series. And then you look at the equations giving you conditions for being a two-core cycle. These equations gives you a full set of conditions at each order of H. And then reading these conditions, you find that the first order in your expansion of the two-core cycle by zeta is it gives rise to a Tuco cycle for this tangent Lie bialgebra. And then, in order to compare this level with this one, you just compute what is the new Poisson bracket that I find out of the deformed quantum group. This is the general recipe now applied to this modified product. And then the computations tells you that you are finding exactly the deformations of the old Lie bracket by this Tuco cycle. So again, it's a matter of bookkeeping. Essentially, we expected to find this kind of results somewhere in literature. We looked for them, we couldn't find them, and apparently they should be known, but apparently they were not, or at least nobody wrote them. Okay, now for the tough cases where we really found something new and original, let me say. Okay. Okay, let's say we are deforming now function algebras by twist and universal quantum algebras by Tuco cycles. In both cases, what's relevant for my quantum object is that it is either commutative modulo H or co-commutative modulo H. In both cases, we are not changing the structure which is commutative or co-commutative modulo H. So for sure, we do know that the deformed object will be again a quantum object of the same nature. So this is something which makes life easier, if you want. But if you apply a deformation by twist or by Tuco cycle in the usual sense, you're sure that taking the limit, everything will just vanish because we are ending with commutative or co-commutative objects for which we know that deformations of either kind are trivial. So it makes no sense to apply this usual technique in this case. The nice point is that you can force the recipe and end up with something non-trivial. So we called these objects polar twist or polar Tuco cycles, and we'll see why. Let's start with the easiest case, the one of polar twist. I take a quantum formal series of algebra, and I want to introduce a polar twist. A polar twist will be an element of this form. So the exponential of some element in my algebra, the tensor square of my algebra, but now instead of multiplying by h, I multiply by h minus 1. So this is the reason for saying polar, because we have a pole at h. But now this makes no sense. You cannot divide by h. Well, you can if you enlarge the scalars in this way. But then you have a problem. If you take formal series, okay, convergence is assured by default. But if you are divided out by h minus 1, and then you are taking an exponential, then it's really, you're, say, traveling at warp speed in the wrong direction, essentially. So this object doesn't look at something living here. Okay. Same problem if you try to do the same at the dual level. I start with a quantized universal envelope in algebra. I wish to consider a Tuco cycle, but now I force the recipe. And so in my recipe, I take an object of this form, but with an h minus 1 instead of an h. The star is again the convolution product. So this is essentially the same recipe in the dual category, say. Okay, so again, this object a priori does not make so much sense. You can write things so that it does make sense, even at this level. Good. But the point is that the recipe of deformation still works with this generalized object, but now it will give non-trivial outcomes. Let's see again for the case of polar twist deformation. So I have my quantum formal series of algebra. I take this ideal, this augmentation ideal. This is the one, if you forget the h, you imagine you are in a classical setup. This is the ideal, the local ideal at your identity element. So it defines the cotangent space. Here is the cotangent space, which is your cotangent Lie algebra. Great. So the tensor square will be given by this coset space. Now, my twist element is a polar twist of this form, as given before. And here I'm taking its antisymmetric part. Then the point is, if I write down the recipe for deforming the coproduct by twist with this would-be twist that I call polar twist, I take my F. And my F, I'll take it here. Now I'm applying this conjugation via an object which is not here. It is in the scalar extension with the Laurent series. So in principle, it will live outside of this. But if you perform computations, then you end up again inside here. Essentially, through the conjugation, the pole disappears, and then the series in H becomes a series in the J-adic topology, where J is the augmentational ideal. So it makes sense. Both problems, the existence of a pole and the convergence problems, are solved. So this object makes sense, which means that you can still define a deformed coproduct, which will have all nice properties of a coproduct. And so you end up, again, with a deformed Hopf algebra, even though the deforming object, the twist, is now a polar twist, which is a generalized object. But this is what allows you to find non-trivial result. And then again, you look at the first order of your twist, which was this phi of A. You look at what it gives at the semi-classical level. It defines something inside here, which would be a twist for this cotangent by algebra. And then again, now we can compare the outcome, the semi-classical limit of this deformed quantization, with the deformation of the semi-classical limit, and you end up with an identity again. So here you have deformation at the quantum level followed by specialization. And here you have instead specialization, you end up with G, and then it's followed by deformation. So again, deformation commute with specialization.
On the slide, so the half bit close. You're not asking for the phi A to vanish in order H bar 0. So this can have some non-zero contribution.
Your phi A, what survives, or your phi, is just, you see, it's part modulo H. And this ends up in here, say in FH J tensor square. Then you take a modulo of this part.
So you're saying, okay, you take this phi A,
yeah,
as something in H bar equals 0. So then you build this exponential with H bar minus 1. So now you have some series where you also like negative powers, H bar. You're saying for this coproduct that you define now, these negative powers are not there. So you only have the...
we'll see later. I mean, they disappear in the computation at first stroke, essentially. It's pretty, I mean, it's hard to read here from the final outcome, but it's pretty clear what happens when you take it by hands. Okay, just me quickly, because here it's more obscure what happens. It's essentially the dual story that you can treat independently. But let me just look at least at the statement. You have now a quantized universal enveloping algebra. You are taking a polar two-co-cycle as I defined before. Now the point is, okay, I have these two-co-cycles. I wish to use it to perform a deformation of my original quantized universal enveloping algebra. Okay, the point now, again, is that in this case, you can certainly compute the deformation procedure. Again, the outcome might be outside U of H. In principle, it is inside here, but it might be not inside U of H of G. But the computations tells you that you're still inside there. So if instead of looking at the outcome for this bigger object, you look at the restriction for this object, you find something which is, again, the same as a coalgebra, but with a modified product. If you want, here, you are introducing a new deformed product. This product restricts to this part. So if you take the new multiplication given by deformation by the two co-cycle, you apply only to this part, you end up again inside here. And then it makes sense to consider this object at the semi-classical level, and it ends up, it ends up being a two co-cycle for the Lie algebra. And again, if you compare specialization after deformation with deformation after specialization, you end up with the same. Okay, this is not relevant. Yep.
What's the Q part of this new object?
What's new? What's new?
No, what is the Q version of this map?
Okay, let's put it this way. 29 years ago, I did this for some R matrix, and it was the R matrix for the UQG by Jimbo and Lustig, written in terms of Q divided powers and so on and so forth. And it works. I mean, up to here again, when you write the R matrix, well, you have to choose integral form. It's a bit long. But anyway, you have an adapted version to quantum groups a la Jimbo-Lustig, say. Okay, let me summarize what happens with this overall picture. Let's say you look at quantized universal enveloping algebra. At the quantum level, for this Hopf algebra, only twist deformations make sense. It is co-commutative, so two co-cycle deformations do not make sense. However, for the Lie algebra, for the Lie algebra, both deformations by twist and deformations by two co-cycles do make sense. So somehow, at the semi-classical level, we can move leftwards and rightwards. At the quantum level, the deformation by the same name, the twist deformation here, okay, makes sense, it works, nice, okay. The deformation by two co-cycle gives you trivial results. So you do not recover this situation. But you do if you extend the notion of two co-cycle to the notion of polar two co-cycle, because you are exactly forcing enough poles of H so to recover something non-trivial at H equal to 0. Whatever standard two co-cycle here gives trivial outcome because it has inside this H which becomes 0. You divide out H twice, essentially, and that's exactly what you need. Necessary and sufficient. And similarly for the dual situation, here what you have is that two co-cycle deformations work fine at the quantum level. They do not work at all at the classical level when you are taking twist deformations. So usual twist deformation at the quantum level cannot work either. But you have twist deformations for the cotangent Lie algebra, and the idea is to lift in a clever way this to the quantum level. And the nice recipe is to use polar twist and perform polar twist deformations with them. Okay, as I said, you might get the results simply by making clever computations. However, what might lead you in these computations? Well, there's an idea underneath. The idea is the existence of this quantum duality principle due to Reinfeldt, which essentially says, okay, most of you possibly are familiar with the idea that, well, UQG is also OQG for the G star, whatever. Okay, this is somewhat rough, even too much rough. Reinfeldt gave a detailed and precise notion of quantum duality, saying that when you're considering quantum groups of either type, you can switch from one side to the other, and this corresponds at the semi-classical level to switching from a Lie algebra to the dual one, or from a Poisson group to the dual one. That is, you are lifting at the quantum level the Poisson duality at the level of Lie algebra or Poisson groups. So in functorial terms, the idea is that you have two functors from the category of quantum formal series of algebra and the category of quantized universal enveloping algebra. I denote them this way. They are inverse to each other. So if you compose twice, you get the same object you started with. And the point is, if you are taking the functor on some quantum function algebra for a given Poisson group, then you end up with the quantized universal enveloping algebra for some Lie algebra. But which one? The cotangent Lie algebra to your original Poisson group. On the other side, if you start with some quantized universal enveloping algebra, okay, this functor gives us fh of something, of some formal Poisson group, but we don't know exactly which one. It will be the formal Poisson group whose cotangent Lie algebra is the initial G. These are maybe 12 lines in Drinfeld papers. And then 2 or 3 papers by myself to explain the story. Apparently, the papers were necessary because nobody had spotted these claims by Drinfeld, which are quite useful, I guess. Okay, let me give a quick idea of how this works. Don't be worried by the appearance. The easiest one is the check for function algebras. So here you have a quantum function algebra. Now let's look here. I'm taking the augmentation ideal. This gives you localization at 1. And when you are taking powers, you're focusing more and more around 1. But now you counter this focusing at 1 with this inverse of h. So on the one hand, you zoom onto 1, you are localizing. On the other hand, you are moving out with this h to the minus 1. Okay, this is something which looks like it's almost a Hopf subalgebra inside here, inside the scalar extension. You need to take completion. And if you take completion, you end up with something which will be a quantized universal enveloping algebra because it's generated by its co-primitive elements, whatever. And by direct analysis, you find out that it is exactly a quantized universal enveloping algebra on the cotangent Lie algebra of the original group, just like it's claimed here. This is the easy half of Drinfeld's construction. The hard half of Drinfeld construction is the second one. Now, you can't see it at once, but this definition is exactly the dual to this one. Just compare union intersections. Here I'm taking powers, but powers over not all the Hopf algebra, just the augmentation ideal. And you divide by, you have to multiply by h minus 1. Here you take this tensor, you take powers of h, not of h to the minus 1. And instead of taking powers, you reverse the construction. You take the inverse of the iterated coproduct. And you also project on the, okay, it's a bit a rush, but just to convince you that there are reasons to believe that these two constructions are dual to each other. It's somehow natural to guess this one, maybe. It is indeed. It is not that much to guess this one. But if you think that you are cooking up something dual to this, then you can find it. Great. So what's the idea? Let's say I'm taking a quantum formal series of algebra, and I want to perform deformation by some polar twist, this one. Let's consider this object given by Drinfeld's functor. Okay, we know that this is a quantization of the type of a quantized universal enveloping algebra for the cotangent Lie algebra. Great. Now, this object is achieved essentially by rescaling this one, because I took the augmentation ideal, I divided by h to the minus 1. And then I took what was generated algebraically by this object. Then if you look at the definition of polar twister, quick enough, yeah. Here it is. You see here, there's this h minus 1. This phi, since f is a twist, this phi must live inside the tensor square, not just of this gadget, but in the tensor square of the augmentation ideal. So you have twice the augmentation ideal here, and only once h to the minus 1. So if you rewrite this object in terms not of fh, but in terms of fh check, you can write here twice h to the minus 1, which means that this becomes h to the plus 1. So in the end, what I'm quickly sketching is that whenever you consider a polar twist for this object, this is also a standard twist for this, which is a quantized universal enveloping algebra. And we do know how to treat standard twist and deformations by twist for a quantized universal enveloping algebra like this one. That's the easiest way to treat the situation. So now you track the construction. So you perform your deformation by twist for this object, but then you recall that what you're interested in is not really this object, is the original FH which sits inside here, and you check that actually the construction restricts to this subalgebra and everything's fine, and you get exactly the statement in theorem 3. So this explains why it's not coming out of the blue. It's coming out of something more, something deeper, which is the existence of Drinfeld functor for this kind of quantum groups. Okay, and the dual constructions gives you the dual situation, but it's much harder to understand in a sense, because algebraically it's perfectly equivalent, just a dual. But seeing it with our eyes acquainted with geometric constructions, it's a bit harder, at least for me. Possibly for people familiar with Hopf stuff, it's not that hard. Okay, last, I think I have till 5:05. Great. Okay, so at the end of the day, the key step is the following, which in a sense comes out of the definitions. The definitions are given exactly so to get this. The key step is realizing that the polar twist for this object is actually a standard twist in the usual sense for this object, which is a quantized universal enveloping algebra. At the other level, taking a polar 2 cocycle for this quantized universal enveloping algebra is essentially the same of saying, okay, the same object now for this, which is a quantum formal series of algebra, is a 2 cocycle in the usual sense. So you know how to treat these objects. Okay, so we just need to check this. We'll do it for the first case, which is quite concrete. So let's say you have this setting, a given quantum formal series of algebra. Just think of OQG if you prefer, and a twist. But now this twist is a polar one. You might read this object as being exponential of phi divided by q minus q to the minus 1, if you like. It will be the same story. Now we have this formula for the deform coproduct. How do we process it? Okay, let's say we are considering this deform coproduct, whatever it means. Now the standard recipe tells you that the adjoint of something, which is the exponential, can be written in a, okay, no, this is the first step, too slow actually. Now my twist, my polar twist f lives inside here. This topological tensor product is the same as this object. So this is again a quantum formal series of algebra, but over the bigger group, which is the G times itself. Good. So now what I'm considering here in step 1 is something which has to do with an object F inside some quantum formal series of algebra like this, and it is you have to perform adjoint action. Good. So the key point is this lemma. Let's say we have some quantum formal series of algebra. In particular, it is commutative modulo H. Then you are taking an object of this type in the square of the augmentation ideal. And then you have this formula. Why do you have this? You see, I have here h to the minus 1. So even forgetting the exponential, taking the adjoint action with L apparently should not give something inside here because you are dividing out h. And then you are even taking the exponential. So two kind of problems. But just look, what's this adjoint action? Is the bracket. But my algebra is commutative modulo h, so this bracket is inside here. So I am allowed to divide out by h. And I get something which sits inside here. So at least before performing exponential, I got rid of this problem of dividing by h at first step. Then there's the exponential. For the exponential, the guy here, phi, lives inside the square of this augmentation ideal. And now you're taking adjoint action with something of this type. Now, with just one single copy of J, you again falls inside J. Inside phi, you have twice of them. So at the end of the day, you end up with this condition. So every power lands you inside the successive powers of the J, the ideal J. And so if you're taking exponential, you're taking a series, but this series is an infinite sum of objects sitting inside farther and farther powers of J. So this is convergent in the relevant topology, the J-adic topology, whose limit is exactly your quantum formal series of algebra. So you see, just by hand computations. Okay, now you have this formal identity. The add of an exponential is the exponential of add. And so I'm done, essentially. And then you apply all these steps to the algebraic group, which is G times G. So this is the summary, if in a sense, where it is, here it is. This was my recipe. I'm applying add of some exponential, which is exponential of add. But now I know that this exponential ends up inside here, and so I'm done. For comatrix, in just 1 minute, what is an R matrix? Well, essentially, it's a twist plus additional condition. And the dual notion, which is not so much used, is that of dual R matrix or Rocco matrix, which is 2 co-cycle plus additional conditions. And then you can apply our constructions to these situations, and you end up with this. Let me put it here. Okay. The generic R matrix normalized will be 1 plus something, so you can write it exponential of h to the something. The something will be a classical R matrix. Now we are considering this generalized notion of polar R matrix or the dual polar Rocco matrix. Now the point is this result, due to, say separately to myself and to Enrique Salbu, essentially being an R matrix for U of H is the same as being an R matrix for the quantum formal series of algebra arising from the Drinfeld functor. And you have a similar dual result for comatrix. Why should one be interested in this? Because with R matrices, you have triangular structures. With polar R matrix, you end up having quasi-triangular structure, which means you have not the R matrix, but you still have its adjoint action somehow. And that's what we are keeping here. So the end of the story is, if you have a quantization which is of a universal enveloping algebra, the first case, which is triangular because you have an R matrix given a triangular structure, then if you apply the construction by Drinfeld. You find the quantization of the dual Poisson group, but it is also endowed with an additional structure, which is a quasi-triangular structures given by a polar R matrix. And similarly for a dual setup, okay, people studying quasi-triangular structures are interested in their semi-classical limit, but this is more for specialists. Okay, I think that's enough. Let me just mention that. No, okay, nothing serious. Okay, that's all. Thank you very much.
Thank you very much, Fabio, for this very nice talk. Are there any questions or remarks?
It was in your
Yes,
thesis.
Giovanni.
I was wondering if you know about this transmutation construction by Majid, and since I guess an R matrix is a twist plus some other condition, I was wondering, so this transmutation takes a quasi-triangular of algebra, so with an R matrix, and modifies the coproduct. Is this obtained, if you know this, just by doing the conjugation by the twist, so by the R matrix on the coproduct? Because I know or is it a different construction?
I don't know whether it's the transmutation, but when you consider triangular structures, you say there is an R matrix. And the R matrix, among other things, is such that the conjugation of the coproduct gives you the opposite coproduct. So it tells you that the deformed coproduct using this special twist is not anything. It's just the opposite coproduct.
Ah, okay. So no.
Maybe that's what he calls transmutation.
No.
It's not.
Okay. Yeah, it's one of the properties.
So you had this statement in the previous slide that you get from a triangular of algebra a quasi-triangular one.
It's triangular for a different object.
Yeah, it seems surprising because triangular are in some sense classical and quasi-triangular are quantum. Yeah, symmetric and braided.
Yeah, the point is
categories of.
But the point is, once you have the quasi-triangular structure, instead of having an element, what you still get is the adjoint action by this element. So the definition is you have a braiding with some additional properties, which gives you downstairs a braiding on the Poisson group G star with additional properties with respect to the Poisson structures. And then this gives you something for G connected to G star and vice versa. But at the end of the day, in this construction, you have an R matrix here, and then you have a classical R matrix downstairs. You have a polar R matrix here. You have a quasi-triangular structures downstairs. The quasi-triangular structures downstairs and the classical R matrix downstairs gives rise to morphisms of this type. At the end of the day, they are the same or the dual to each other. So in the end, you are using the same kind of informations under different disguise. If they are all coming from the original R matrix, I mean.
I see. Okay, but it seems like some kind of source of quantumness that if we looked at representations of the thing on the left, this would be a symmetric monadic category, and modules for the right one would be braided monadic category. Is there a simple example where this non-commutativity?
Yeah, you have examples for. I mean, you have this construction for SL2 to begin with,
okay.
And then with all semi-simple algebraic groups.
And so what do you take as
the quantum and so on?
But there you need to choose a triangular R matrix, right?
You need to choose a quantum R matrix, yeah. Well, you have the standard one.
But I thought you choose a triangular one on the right.
On
the left.
No, I mean, The Hopf algebra is triangular. Triangular means, oh, maybe you call it quasi-triangular.
So for me, okay, triangle.
Oh yeah, triangle is when the R matrix is unitary, symmetric,
Yeah.
whatever.
Yeah.
Oh, okay. No, it's a mistake. Just a mistake of
It should be quasi.
terminology. See, quasi-triangular.
It should be quasi. Okay.
And then and then quasi at the left. So it's pseudo.
Yeah.
No, I don't remember. It's due to Reshetikhin introduced the terminology, and I used the same. But now I forgot.
But it means
I was pretty sure it was quasi-triangular, but it was wrong.
Oh, but so you don't have like R matrix as an element, but the category is still braided. That's the distinction. Okay.
Yeah.
Okay. Thank you.
By the way, this works with R matrices. I think it can't work with twists in general, because in the proof Albu and myself had treated the case of a general quantum R matrix, which acts by a joint action, and we looked at what happens when you take the Drinfeld functor. And your object, your R matrix, does not live inside the result, the outcome, but the adjoint action still lives there. So it makes sense. We missed one step, and the one step further was done by Enriquez Albu, which found that this R matrix actually is automatically a polar R matrix for the Drinfeld functor. And that's, in this case, you explicitly use the additional condition of being an R matrix. And already in our proof of the weaker result with myself and Albu, we used that fact. So I think you cannot extend it there's no something like every twist for an object is a polar twist for the Drinfeld functor. This is specific of R matrices.
How should one think about the polar objects, maybe from the categorical perspective? Like, they are not about the limit of h bar going to 0, obviously.
Yeah.
Are they about? So there is the crystal limit, which is what? Like q going to 0, which is like h bar going to minus infinity.
No, the crystal is q going to 0. Not
Yeah. So h bar going to minus infinity.
Yeah. I could say whatever. I mean,
okay.
That's real insight. So.
Entry question, because I'm much more comfortable on the Q side. But I mean, basically, seeing multi-parameter that are up there. One example, if I were to take OQ of G and do the twist, then an example of this would be that I would go from Q to multi-parameter. Is that?
Yeah.
That is very.
Actually, we came out with this kind of study because it's the, say, generalization of what we met working with quantum groups. Quantum groups, say, over symmetrizable Kac-Moody algebras. And we originally worked with the Jimbo-Lustig version. And then in that case, it's interesting because you have two kind of communities. The community working with quantum group a la Drinfeld, say, UH of G. Well, this is a quantum version of UG, so we look for deformations by twist, because for UG, only deformations by twist makes sense. And so they consider twist, they consider R matrices, and all this kind of stuff. People working with quantum groups a la Jimbo-Lustig instead usually work with deformations by two co-cycle. And the reason is they use a special kind of two co-cycle, which is of toral type, we call it, because it's, a two co-cycle should be defined on a bilinear function on your Hopf algebra. Actually, in this case, it is focused on the Cartan part of your quantum groups. But in the Jimbo-Lustig quantum group, the Cartan part is not really of the universal enveloping algebra type. It's rather of the function algebra type. It's a quantum torus. You have a Laurent polynomial algebra. And that's why, essentially, in that case, the two-co-cycle construction works, because they are somehow cheating without knowing. They are applying a two-co-cycle construction on something which is of mixed nature, but where the construction actually works is on the quantum function algebra side of their quantum objects. But these two communities never talk with each other. So when starting consider the deformation theory for quantum groups, there is this construction, there is this construction. And we thought that there should be two different kinds of deformations, two different theories. You can mingle them together. Well, at the end of the day, you realize that the construction of deformations by two co-cycles that they do with the UQG type quantum group, so involving generators of type k plus to the minus 1. This k, they are exponential of h bar times something. So if you try to write the two co-cycles that they used in terms of the Drinfeld type quantum group, you have to divide out twice by h bar. You have one h bar above, so in the end, you end up with an h to the minus 1. So you end up with a polar two co-cycle. But this polar two co-cycle does work on the original object. So we found it out of, say, experimental data, which were already available, but you had to look at them in a proper way. So this, in the end, is a great source of examples.
And so to bring it down even more concrete again, like if you take OQSU2, so okay, I'm going to stick with Q and ignore that H exists, right? But if I perform this, then I would get something in the simplest case that would be a deformation in terms of Q and P. How do the representations, the finite dimensional co-modules or modules look? Do you get more of them? So for OQSU2, the usual, you're going to have one for every inch.
Here, there's another key result, which is not there because it's not true in general. And the point is, okay, let's step back to UQG. Yeah, UQG, okay? Let's say you can perform deformations by twist or by two co-cycle, polar two co-cycle. Well, in that case, you have a problem with twist because you have not this formal series expansion, so you have to write them properly. But you can do it. We have a paper, the first paper was in that language, so you can handle it. It's a bit messy, but you can. So you have two theories. But then there's a crucial result that tells you that, you know what, if you perform a deformation by twist, then you can realize the same Hopf algebra as a deformation by two co-cycles and vice versa. Actually, this amounts to change the presentation and nothing more. You slightly change the generators. You renormalize the Chevalier generators. And so changing the generators, the relations change. But if you take one presentation, you have the old product and the new coproduct because you are taking a deformation by twist. If you change the presentation, you have the old coproduct, you have a new presentation, a new algebraic structure. But so we might say, if you modify the coproduct, you are changing the tensor structure in the category. Yeah, but the Hopf algebra is isomorphic to that one, which has a different algebraic structure and the same tensor structure. So it's
the category is staying the same.
yeah, but I didn't went to the end, but the point is, whatever your deformations, you are always ending up with the same objects, but you're reading them in different ways. Our problem is that we work with these objects as given by presentations and relations, which is artificial. You are choosing a specific point of view. In this case, depending on the presentation, your models present themselves in a different light. So you have to, yeah, but maybe the same scene a different way, it's still meaningful. So I'm not sure whether this is an advantage or a source of confusion.
I also have a very short question. Can you go please to slide 4?
Should I ask for an increase in my fee?
Not sure. So yeah, my question is, so if you have a Lie algebra attached to it, so you can, consider the universal enveloping algebra or also the universal enveloping coalgebra. Basically, you perform the same machinery in the dual way. So this is a commutative of algebra, is of Poisson, and so on. My question is how this object enters in this duality. So if it's connected to.
And my question is, what is exactly this? How do you call it? Co-universal enveloping algebra?
Or universal
It is the
enveloping
shuffle algebra with
coalgebra?
some no.
It's okay. It's quite involved, but it's basically reversing arrows for universal enveloping algebra.
Yeah. So if it's theoretically categorically dual, it should be essentially the same as a universal quantum formal series algebra.
That's my question, but I'm not sure.
Yeah.
Okay. Yeah. Sure.
So at the end, we have seen these polar R matrices. So what happens when you twist a polar R matrix with a polar twist?
Well, in general, twists.
Usually
you can compose twists, correct? Yeah. So if you perform a twist of a triangular Hopf algebra, you have a new triangular Hopf algebra with a different R matrix. I'd expect the new R matrix to be polar again, because I mean there's this factor h to the -1, which will not.
Would make sense, right? Because in a way it's built in a similar way. So the new R
Wait.
is also like
wait.
If you are -1 or f op -1. Yeah?
If you are twisting by a standard twist, okay, for sure it stands the same. If you twist by a polar twist, you should write a formula for the new R matrix. Is it a product of several exponentials having all?
No, it's conjugation by the twist, right? It's F
Again.
R F inverse.
So it's
again, yeah, it's the rule for.
Yeah, it's very similar to the coproduct. Just you have one extra flip, so there's F R F minus.
It's exp add of h to the -1 phi applied to your h to the minus r. Well, it should work again.
Probably.
Yeah.
Okay, thanks.
It should be exactly the same computations, but one small step further. Should run it. Should work.
Other questions or comments from the online audience? If you have some, unmute yourself. Then if it's not the case, let's thank Fabio again. And I hope we will see you next week for next seminar. For
Rita Fioretti is announcing, thanks for the talk. Goodbye.